Hi everyone, I'm Chen from the University of Queensland. Today I will be presenting our work, Rethinking Generative Virtual Learning, an ensemble learning perspective for recognizing visual patches. This is a joint work with Wang, Jingjing and Huang. Virtual learning is the task of recognizing instances of unseen classes, solely based on the semantic information of the classes, without any corresponding visual examples during training. In other words, the training data will contain 0 visual examples of the unseen classes. Further, the seen and unseen categories are mutually exclusive. The state-of-the-art direction for virtual learning is generative virtual learning, which synthesizes visual samples for unseen classes to perform supervised classification. Traditional generative virtual learning frameworks use a global generation paradigm, which extracts the ground truth visual features and generate the fake visual features as a complete component. Some of other existing methods leverage detection model to extract the patch visual features, specifically the semantic parts like the head, tail, breast are firstly detected, and further, the backbone extracts the visual features from the detected parts. The visual features of several patches are then concatenated as a complete component and treated the same as the global generation paradigm. These two generation paradigms, global generation and patch generation, are limited to background noise and waiting for importance issue. We propose a new learning paradigm for generative virtual learning, multi-patch generation. We extract patch visual features and leverage multiple generative models to generate visual features for corresponding patches. After that, we use the pre-computed attention weights of different visual patches to make the final prediction decision. The overall framework can be illustrated as 6 parts. The generative model adopted in our model is water-sustained generative adversarial nets, WGAN. First, the raw textual descriptions are embedded as TF-IDF representations as the class-level semantic information. The TF-IDF representations are then denoised as clean semantic vectors. The next step is to generate visual features of a semantic patch using the generator. We have multiple generators here, each for a corresponding patch. In our discriminators, we have the WGAN loss to discriminate true or false the fed-in visual features are. And the classification loss is to classify the fed-in visual features to a corresponding class, which makes them generated visual features more interclass discriminative. In the classification stage, we train a classifier for each patch independently. With the trained classifier, given a test sample, we yield a probability distribution of each patch of the test sample. We have computed the attention weights of the patches to weigh the importance of each patch. Multiplying by the weights, the patch probabilities are stacked together, and we pick the highest score as the final classification decision. As for the attention weights, we propose an offline algorithm to compute the importance of the visual patches. It's essentially interclass and intraclass distance ratio of the specific patch. So, if the visual features of a patch are more interclass discriminative and more intraclass centralized, the weight of the patch is larger, and vice versa. We validate our proposed method on 2 datasets, CUB and NAB, and use average per class top 1 accuracy as the evaluation metric. Our model consistently outperforms existing state-of-the-arts. From the ablation study, we show each component of our method is significant to the performance. The T-SNE visualization demonstrates that generated visual features can capture the rough distribution of the real visual features. We also did a virtual learning retrieval on the 2 datasets and achieves state-of-the-art performance. Please feel free to contact us if you have any questions. Thank you.